This is the final part of the Getting Started with FRS training, in which we will go through the different interfaces of FRS as well as the selection of the FPGA chip. First, we will go through the different types of Ethernet interfaces that can be used with FRS, like MII, GMII, SGMII, RGMII 1000 base X, and 100 base FX. Then we'll present the other interfaces FRS has. After that, we will move on to FPGA selection guidelines, and finally on to how to proceed with your implementation process from there. The Ethernet interfaces provided by FRS natively support MII and GMII standards. Support for other standards is provided by interface adapters that convert the native interface of FRS in the another kind of standard Ethernet interface. Different Ethernet interface adapters are provided by Flexibilis and Altera. Customers and third parties can also implement their own adapters. MII and GMII interfaces are native in FRS, and the MII and GMII for a port share the same interface signals. A different clock speed is used for all three speed options: 2.5 MHz for MII at 10 megabits per second, 25 MHz for MII at 100 megabits per second, and 125 MHz for GMII at 1 gigabit per second. The direction of the transmit clock signal towards PHY is different in GMII and MII modes. Because of this, and also because it's reasonable to generate the high-speed GMII transmit clock outside of FRS, FRS employs an external clock multiplexer. The clock multiplexer is not needed if the port is forced to a fixed speed or if it's connected to MII only physical layer chip. Phase locked loop, or PLL for short, is a component inside FPGA that can be used to generate faster or slower clocks from the FPGA input clocks. When connected to an external PHY chip with MII, the needed clocks come from the PHY. When MII is used in FPGA internally, for example with an interface adapter, typically a PLL is used to generate the different clock speeds. The clocks can be brought straight to the FPGA pins also. Note that the external input clocks need to be routed into the dedicated clock input pins. A trial FPGA compilation verifies the suitable pins. To implement an RGMII interface, an RGMII adapter is required. The adapter changes the native MII or GMII interface of FRS to an RGMII interface that can be connected, for example, to an external PHY chip. The clocks needed are the same as with MII and GMII: 2.5 MHz for 10 megabits per second, 25 MHz for 100 megabits per second, and 125 for gigabits. A clock multiplexer is needed if the port is not forced to one single speed setting. The RGMII RX clock needs to be connected to a dedicated clock input pin of the FPGA chip. A trial compilation is recommended to verify the pin locations. SGMII or 1000 base X adapter changes the native Ethernet interface of FRS to either SGMII or 1000 base X. The interface type can be changed on the fly between SGMII and 1000 base X, which makes the adapter handy when used with SFP modules. This is because fiber optic SFP modules require using 1000 base X, and copper SFP modules can do lower 10 gigabit speeds only when using an SGMII interface. This adapter employs an Ultra IP block named Triple Speed Ethernet Megagirl function, which needs to be licensed from Ultra if used in a design. Note that the Cyclone V FPGA has a feature that reserves at least one extra transceiver channel to create the transmit clock. Because of this, the one channel can't be used as a transceiver for SGMII, 1000 base X, or 100 base FX. A trial compilation is much recommended before, for example, designing the PCB layout. Cyclone IV doesn't have this sort of limitation. The Flexibilis 1000 base X adapter provides a conversion for GMII interface to 1000 base X interface. It is much smaller in size than the SGMII 1000 base X adapter presented in this previous slide, but this adapter does not provide SGMII. The adapter can be used when a gigabit fiber optic transceiver or an SFP module is connected directly to the FPGA. Also, copper SFP modules are supported, but only with gigabit speed. No license is needed to be able to use this adapter. The adapter needs just one 125 MHz clock, and it uses the FPGA transceivers. Note also the Cyclone V transceiver channel usage limitations. For 100 base FX fiber optic transceivers and SFP modules, there is a 100 base FX adapter. The adapter needs only a single 125 MHz clock, and it uses the FPGA transceivers. The Cyclone V transceiver limitation applies, so a trial compilation is recommended before hardware design. As the name implies, 100 base FX is 100 megabits per second only. If you want to access the register of an SFP module, you'll need to connect an I2C interface to the SFP module. The I2C interface can be provided by an IP block on the FPGA or by an entity outside of FPGA. An I2C access from the CPU to the SFP module is needed, for example, when you want to use lower than gigabit speeds on a copper SFP module. Typically, you want to access the register of the physical layer chips you have in your design. This is done by using MDIO. In a typical design, the CPU pulls the statuses of the Ethernet interfaces from the physical layer chip, for example, the negotiated line speed, and configures the Ethernet interfaces of FRS accordingly. Next, we will move from the Ethernet interfaces to the other interfaces of FRS. In addition to the Ethernet interfaces, FRS has a few other interfaces. These are the authentication interface, Avalon slave interface, and time interface. The authentication interface is connected to an external FPGA security chip. This is the method FRS uses to make sure the user has a valid license to use FRS in their product. For evaluation purposes, FRS works also without the security chip, but only for a couple of hours, after which a reset is needed. The Avalon's live interface is for accessing the registers of FRS. Typically, the registers are accessed by an FPGA internal software processor or by a CPU on a separate chip next to the FPGA. A bus bridge is used to make the register interface compatible with the interface used by the CPU, for example PCI, PCI Express, I2C, or MDIO. The time interface is used for communicating exact time information for FRS. The information is kept in a real-time clock outside of FRS. FRS requests the clock time using the time interface when it needs it for IEEE 1588 supporting purposes. FRS has separate clock domains for the FRS core, for Avalon interface, and for the transmit and the receive sides of the MII interfaces. Typically, there is one oscillator on the board. The clocks needed by FRS and by the other FPGA blocks are generated at the FPGA with PLLs. Exception to this is the Ethernet receive clocks that come from the line in case of external Ethernet interface. For each separate clock domain of FRS, there is a reset signal. The reset signal resets the logic of the corresponding clock domain. For the clock domains whose clock come from a PLL, the reset signal is typically driven by the PLL locked indication output of the PLL. FPGA chips have dedicated inputs for core and I/O operating voltages. The core voltages vary depending on the FPGA type, and the I/O voltages depend also on the I/O standards used in the design. The I/Os are divided into a few separate banks, and the I/Os in a bank share the same I/O voltage. The power consumption of the FPGA chip can be estimated with Altera tools. The FPGA configuration is volatile, and therefore the configuration bit stream has to be loaded onto the FPGA after every power-up. There are several different ways to do the loading of the bit stream. The FPGA can, for example, fetch the configuration bit stream automatically from a dedicated configuration flash chip. Another alternative is to do the writing of the bit stream to the FPGA by an onboard CPU. In this case, the bit stream can be located in the same flash memory as the software of the CPU. This may bring savings in the hardware cost because this will result in one less memory chip on the printed circuit board. The software and the FPGA configuration bit stream can also be distributed together, which guarantees that the software version used is always compatible with the FPGA configuration version. In some cases, for example when using PCI Express, the FPGA functionality has to be up fast after power-up. This forces to use FPGA configuration methods that are fast enough. The clock signals connected to the FPGA should always be connected to the dedicated clock input pins. In case of FRS, this includes the clock from the onboard oscillator and the interface receiver clocks. Note that the FPGA built-in transceivers have their own dedicated clock input pins. So, if the FPGA built-in transceivers are used, a reference clock should be connected to the clock inputs. Transceivers are used, for example, with SGMII, 1000 base X or 100 base FX interfaces. Next, we will go through a few things to consider when selecting the FPGA chip for your design. The most recommended FPGA devices for FRS are Ultra, Cyclone IV and V. The Cyclone family represents the low end of the Ultra FPGAs, providing the lowest cost and the lowest power consumption. If you are going to connect fiber optic transceivers directly to the FPGA, or if you are going to use SGMII to connect to your physical layer chip, you will need to select an FPGA chip that has built-in transceivers. This means you should choose GX, GT, SX, or ST family. Models without transceivers are E and SE family, and you can select them if you do not need high-speed serial interfaces. The recommended devices from Cyclone IV GX family are EP4CGX50 or bigger. From Cyclone V GX, GT, and SX families, from 5CGXC5, 5CGTD5, and 5CSXC5 upwards. The Cyclone V, SE, SX, and ST families include an ARM-based hard processor together with the FPGA fabric. Since you probably need a CPU in your system anyway, this is a good alternative to a separate CPU chip. The integrated processor is a dual-core Cortex A9 running at 925 MHz, and it is able to run, for example, Linux operating system. SE version is without transceivers, and the transceivers in SX version are fast enough to support all gigabit Ethernet standards. Transceivers in ST version supports transfer speeds up to 6.144 gigabits per second, which is far more than enough for gigabit Ethernet. An FPGA family typically consists of tens of chips that differ in the package types and the amount of logic and other resources they offer. The FPGA chip resources include, for example, logic elements, embedded memory, multipliers, PLLs, internal clock networks, and user I/O. It is a little challenging to estimate the final resource consumption during the product development, so it is recommended to use devices that are large enough in the prototyping phase. FPGA devices in the same package are typically pin compatible, which makes it possible to change the FPGA device to a smaller one later if the resource consumption of the final logic is low enough. Tryout compilations are always recommended before the final device selection. Typically, one FRS instance on the FPGA is enough, but for Quadbox you'll need two, which significantly increases the amount of FPGA resources consumed. The number of Ethernet ports affects the amount of resources consumed by FRS. FPGA resources are also consumed by interface adapters, real-time clock, optional NIOS processor, and so on. In many cases, customers' own or third-party logic is also fitted into the same FPGA. Select pin-compatible devices and design the pinout so that you use only the I/O that is available in all the devices you might change later to. The Cordus tool provides assistance with this. Please also remember to take into account the other possible license fees. The NIOS 2 soft-core processor and the triple-speed Ethernet Megagore function can be licensed from Altera. The MicroC OS 2 operating system is property of Microum, and AFEC can be licensed from Flexibilis. The next step is to specify your system and your requirements, like interface types, port count, and whether you need time synchronization functionality. You also have to decide, do you need other software with our HSR PRP functionality, and where are you going to run the software? Then, you should select the FPGA device to be used, after which you can try to compile the FPGA design for the first time. Make the design pin compatible with other FPGA chips in the same package, so that you can change the device. The tryout compilation gives you an idea whether you can fit all that you need onto the selected FPGA, and whether your pinout is feasible. These 5 parts of the training were the training module 1. The training continues as an interactive online training with module 2, in which we will check and validate your design against your requirements. For that, we will need the specifications and the requirements for the related parts. These will be reviewed by a team of FPGA and hardware experts. Also, an FPGA compilation tryout to verify pin locations will be made by us during the module 2. Please contact us to ask for an offer for this part of the training. The contact link is in the description of this video. The final part of the training, module 3, is about implementing your final FPGA design. Schematics for the related sections need to be ready before this module. The outcome is the FPGA reference design ported and compiled to the target environment. The technologies are defined in IEEE Standard 1588-2008 and IEC Standard 624393. Useful links to manuals can be found in the description of this video. If you have any questions, you can contact us at contact@flexibilis.com. This is the end of the training module 1. The next modules are customer-specific, concentrating on the customer's own FPGA design for customer's own hardware. Please contact us for the rest of the training modules. Thank you for watching.